Now, for electrochemical cell notation is given. I want to determine the Ecell, and choosing the relevant half equation for this is very easy. But before that, let us just comment on the cell notation. Remember, cell notation, it is standardized. We write down the oxidation half cell, swap bridge, followed by the reduction half cell. And from left to right, you have to show oxidation, and from left to right, you have to show the reduction. So when you read through this cell notation from left to right, it's just telling us this is an electrochemical cell, and in this electrochemical cell, iron 2 plus is oxidized to iron 3 plus, and Ag plus is reduced to Ag. If I interpret this from left to right, correct? And when we choose the relevant half equation from the data booklet, you notice for electrochemical cell, finding half equation is very simple because both species on both sides of the equation are given. So very easy for me to pick this up. Involving iron 3 plus to iron 2 plus, 0.77 volt. Involving Ag plus to Ag, again fairly straightforward, it is plus 0.80 volt. Because both species on both sides of the equation are given, so it's very obvious. And we also know who is oxidized or reduced. Iron half cell undergoes oxidation, silver half cell undergoes reduction. Calculating Ecell is also simple. Reduction minus oxidation, I get a positive value plus 0.03 volt. Of course, we can also do by comparing E value. More positive reduce, more negative oxidize. So silver half cell undergoes reduction, iron half cell undergoes oxidation, but it's not really necessary because you notice the cell notation already tells me who is oxidized or who is reduced. The process is already given in the question. So this is involving A. Now for part B, we want to predict what will happen to the cell potential when you do certain things to your half cell. So part 1, we add sodium chloride to your silver half cell. Now for questions like this, where we try to disturb the position of equilibrium for one of the half cell, there are 2 layers to it. First thing is we want to determine if you add something to the half cell, okay, what will happen to the E value for the half cell? Once I determine what happens to the E value for the half cell, then we want to take a look at this half cell that changes. Is it E reduction or E oxidation? Then we substitute back to the calculation. Ecell equals to E reduction minus E oxidation. Then from there we determine what will happen to my Ecell. So there are 2 stages to that. First thing is what happens to the half cell. So if let's say for your silver half cell, when you add sodium chloride, there are a few things that are possible. Maybe there's precipitation. Sometimes what we will have is acid base, especially if you add H plus, add OH minus. Sometimes we are just increasing the concentration of one of the species in the half equation. So it really depends. It really depends. So whatever they put in, we consider, is there any of these things that can take place? Is it precipitation, changes of your concentration, and so on? So in this case, if I add sodium chloride, source of Cl minus, it should precipitate your Ag plus, and therefore the Ag plus concentration will decrease. Forms your silver chloride, concentration for Ag plus decreases. If the concentration for this decrease, position of equilibrium will shift towards the left hand side. And if POE shifts towards the left hand side, the E value will decrease. So this is important. This one is important because when there's a shift in position of equilibrium, the E value actually will be affected because E value literally tells me or measures the tendency for the fall reaction. It tells me the tendency for reduction. And this is the first concept that we have talked about when we first started on electrochem. We've mentioned that. We said that E value, the meaning of E value, it tells me the tendency for the fall reaction, tendency for reduction. Fall reaction more likely to occur, E value is more positive. Reverse reaction more likely to occur, E value is more negative. It literally tells me how likely the fall reaction occurs. So when there's a shift in position of equilibrium, favor fall reaction, favor reverse reaction, your E value will be affected. If position of equilibrium shifts towards the right hand side, favor fall reaction, which means that it favors reduction, it will increase the E value because E value measures the tendency for fall reaction. So if the fall reaction becomes more likely to occur, we'll have a bigger E value. Conversely, if position of equilibrium shifts towards the left hand side, that means it favors the reverse reaction. Remember, I cannot favor both reaction. If you favor reverse reaction, you will disfavor the fall reaction. I favor reverse, then I don't like the fall reaction. If I don't like the fall reaction, the E value will drop because now the system likes the reverse reaction. It doesn't like the fall reaction anymore. The E value is expected to go down. So fairly simple. If there's a shift in position of equilibrium, POE shift right, E value goes up. POE shifts left, E value will come down. So we are able to determine the E value for your silver half cell decreases. Then the next thing we do is this E reduction or E oxidation. So if I come back to here, your silver half cell undergoes reduction. So this is E reduction. E reduction decreases or less positive. Sub back into an E cell equals to E reduction minus E oxidation. And therefore, if E reduction decreases, your E cell will also decrease. Now, what is super important is when we consider shift in position of equilibrium, shift left and right, always use the half equation in reduction form. Use the half equation that is inside the data booklet. This is super important. And you notice consistently when we do questions, we always use the half equation wholesale in the data booklet. There's no instance where we ask students to flip the equation. In fact, I've always emphasized just use the half equation wholesale in the data booklet. Don't modify the half equation. Don't go and change the sign. If you have the habit of doing that, then this will give us problem here. So if we are following what is recommended, if we don't have the habit of flipping the equation, then when we do questions like this, it wouldn't even be an issue because you don't have the tendency to modify the half equation. Always use the half equation in reduction form, because when we talk about shift in position of equilibrium, shift left and right, then E value, what does it become? It's all based on the reduction half equation that is in the data booklet. So if for whatever reason you happen to use the oxidation half equation, you shift left and right, the outcome is opposite, then whatever conclusion that you have is all wrong. So don't have the habit of flipping the equation. Again, if you consistently just use whatever that is inside the data booklet wholesale, then there's no problem at all. It wouldn't even be an issue when we do this exercise. All right, so we don't want to bring out all these issues. There are certain things that we will need to standardize. And when we choose or when we make use of the half equation in the data booklet, don't have the habit of flipping the equation or changing the sign for the E value, especially for oxidation. Some of us still like to do that because it's not wrong. That's the issue. If it is wrong, some of us eventually we will just accept, okay, it's not correct. But the issue is, it's not a wrong concept, but if you have the habit, then when we do certain questions, it's going to give us problem. So recommended is we just use it wholesale, then let the formula do the conversion for me. Now, for the second part, involving surface area of the silver electrode is increased by dipping the electrode deeper into the solution. Now, changing surface area actually doesn't really affect E value, because if it does, if you think about it, if it does, then when we consider standard condition, which is temperature must be 298 K, pressure must be 1 atmosphere or 1 bar, concentration of ions in solution has to be 1 mole per dm cube. If the surface area of the electrode in contact with the solution is important, then when they specify standard condition, they should already mention how much surface area of the electrode that must be in contact with the solution. Correct? You notice that's not the case. It means that surface area is not important in terms of affecting E value. And what changes is rather the sensitivity or the responsiveness of the electrode. Because if you have a bigger surface area that is in contact with the solution, you'll be able to establish equilibrium faster. Your instrument is more responsive or your instrument is more sensitive. That means changes to an E value in a solution, your electrode is able to detect it faster. So you'll see the changes reflected in the voltmeter a lot faster. So it affects the sensitivity, but it doesn't affect the E value. Alright, so it doesn't affect the E value. There are no changes to an E cell. Surface area is also linked to the shape of the electrode. So your electrode touching the solution versus the electrode holding it submerged versus whatever shape that you choose, star, circle, moon, square, triangle, whatever shape that you want, it doesn't affect the E value. So this is involving part 2. Next, how about part 3? Solid iron 2 chloride. Now when we're adding iron 2 chloride to your iron half cell, directly we are increasing the iron 2 plus concentration. So again, when we consider shift in position of equilibrium, please use the reduction half equation, which is here. And if there's an increase in iron 2 plus concentration, this one goes up. Position of equilibrium again will shift towards the left hand side. And if POE shifts towards the left hand side, it will disfavor the fall reaction. Again, the E value will decrease. Very, very simple. Again, E value measures the tendency for fall reaction, which is reduction. If position of equilibrium shifts right, favor fall reaction, E value will go up. If position of equilibrium shift left, favor reverse reaction, E value will go down. Correct? So this is involving your half cell. Then the next thing we do is we look at this half cell. Is it E reduction or E oxidation? So iron half cell is for E oxidation. You sub back into an E cell. E cell equals to E reduction minus E oxidation. Smaller E oxidation means you have a bigger E cell. E cell is supposed to be more positive, or you have a greater E cell. And again, super important for us to consider your reduction half equation. For this iron half cell, some of us might just conveniently try to use the cell notation. Because cell notation, the iron 2 plus, the iron 3 plus is there. And we might think that, hey, this is also the half equation. I can just make use of this and I consider shift in position of equilibrium. But you notice this guy, your iron 2 plus is on the left hand side. Iron 3 plus is on the right hand side. It's opposite what we have in the data booklet. Why is that the case? It's because when you write down cell notation, you're supposed to show oxidation. This guy is actually describing this process. Iron 2 plus is oxidized to iron 3 plus, and the electron is on the right hand side. So if you're using this format, that's the problem, because this half equation is in oxidation form. And if you use the cell notation and then you try to consider shift in position of equilibrium, the conclusion is totally opposite what we have here. And the error is because you're using the oxidation version, or you're using the oxidation form instead of the reduction form, which we are supposed to do, all right? Because all this E value is based on reduction. So therefore, please remember to use the reduction half equation. Super important. Just use the half equation wholesale in the data booklet. Don't use other variation. Cell notation, you have to be careful. The oxidation half cell is already written in oxidation form. So if you use it to consider shift in position of equilibrium, you're going to end up with the wrong outcome.